Hey folks, today's screencast is we're going to pick up and finish talking about transformations of functions. In the previous screencast, we talked about shifts, both vertical shifts and horizontal shifts. So check out that screencast for that. Today, we'll talk about reflections and stretches and then inverse functions, which is section 1.6. So a reflection, there are two kinds of reflections, and they're accomplished by introducing a minus sign either outside the function like this or inside the function like this, right? All of our transformations can have sort of two different flavors, one where we do something to the output and the other where we do something to the input. So if we do this, let's focus on this kind of reflection first, right? We put a minus sign in front of the function. The effect of that is, let's say our function is y equals x squared, the blue curve, this parabola. And we ask ourselves, well, what happens if we put a minus sign in front of it? Well, if you go to any input value, say x equals 2, the output on the orange curve is going to be the negative of the output on the blue curve. So whatever this y value is, its opposite or its negative will be the y value on the orange curve. And the way you get to its opposite is by just flipping around 0, right? The y values are all on the vertical axis. So I just go from this y value, flip it around 0 to this y value. And since I do that at every single point, right, no matter where I am, there we go, I'm just kind of flipping around the axis. The effect is to take the blue curve and flip it over the x-axis or reflect it through the x-axis is the way that math books talk about this. So this is a vertical reflection, or a reflection through the x-axis. On the other hand, if we do this, if we put a minus sign in front of the input value, what happens then? And here I'm using a different curve. So this is not x squared. That label is not appropriate. But just take the blue curve f of x. And if we ask ourselves, okay, what should be the function value for this guy, f of minus x at x equals 2? Well, it should be the function value at minus 2. So what I'm going to do is I'm going to flip over to the input minus 2, take the y value on the blue curve, which is this very, very small y value right here, and that should be the y value over here on the orange curve. And I do that at every single point, right? Pick an x value like right here, let's say. And if I want to know what the y value should be on the orange curve, I flip over to this x value, take the y value on the blue curve, and pull it back. So the effect of that is to reflect through the y-axis. So this is a horizontal reflection. And this is, no matter where I put the input, this is what I do, right? I just sort of flip across the input axis to get my new function value. So when I put a minus sign outside the function, negate the output, that's a vertical reflection. When I put it inside the function, that's a horizontal reflection, a reflection through the y-axis. Okay, let's look at a quick example of this before we talk about stretches. So this example, again, comes from, where are the notes and exercises? Oh, I thought I had them out. Find them. Yeah, let's try this. So from the notes and exercises, and this is what, 1.29, I believe the number was. Definition, transformations. Here we go. All right, so I have this, I'm given the graph of a function called g, and I want to figure out what the graphs of all these different changes look like. So there's 4 different pictures I'm going to draw. The first is this transformation, then this transformation, and so forth. So in the first transformation, I'm putting a minus sign outside the function. So that's going to be a vertical reflection, or reflection through the x-axis. And the result of that is this orange curve, right? You can see the x-axis acts like kind of a mirror, and the orange curve is the mirror image of the blue one through the x-axis. On the other hand, if we try to figure out this one, so now I have a minus sign in front of the input, that's going to be a horizontal reflection, a reflection through the y-axis. And so visually, that looks like this, right? So they're on top of each other a little bit here in these flat parts, but you can see that this blue point here gets reflected through the y-axis to this orange point, excuse me, over here. And that's the labels here should be g's, not f's, because the function is g of x. Okay. We can do more than one transformation at once. So in the third example here, we're doing both. We're reflecting through the y-axis and through the x-axis. And the result of that is the picture that you see sort of at the bottom of the screen here, right? So this is the original function, the blue. And if I reflect through the y-axis, only through the y-axis, I get this picture here from up above. And then when I reflect that through the, when I reflect through the x-axis, I get this picture. And when I reflect that through the y-axis, this point here is going to reflect over to here somewhere. And that's the picture you see down on the bottom. This kind of reflection where you do both a vertical and a horizontal reflection is sometimes called a reflection through the origin. So a reflection through the origin is both a horizontal and a vertical reflection. Okay, there's one more, whoops, I want to do that. There's one more in this example, and that is here. Again, I have two transformations going on here. The first one is if I just focus on that and ignore the -2, that is a reflection through the y-axis, a horizontal reflection. And then this is a shift, right? Recall if we subtract 2 outside the function, that moves the function down 2 units. So what I'm going to do is I'm going to reflect first through the y-axis. That's going to give me this orange curve up here. And then when I take this orange curve and shift it down 2 units, what I get is this picture right here, right? So that's the orange curve, the blue curve rather, reflected through the y-axis and shifted down 2 units. Okay, so that's good for reflections. Let's talk a little bit about stretches. There are 2 kinds of stretches, a vertical and a horizontal, and they are accomplished by multiplication, right? So shifts are accomplished by adding, reflections by introducing a negative sign, and stretches by multiplying. And for a vertical stretch, we multiply the output, right? So you can see what I've done here is I've put a constant k in front of the f of x. So this is, of course, k times f of x. And the effect of that is that the outputs for g are the outputs of f multiplied by this number k. So what that means depends on the value of k. If k is a number bigger than 1, so let's take here, I have again y equals x squared is the blue curve. And in the purple curve, what I've done is I've multiplied by some number, 1.545. What happens if you go to an input value now, the value on the purple curve is going to be 1.545 times the value on the blue curve. So it's going to be a little bit bigger. And that has the effect of sort of stretching the blue curve upward. Now, it's not the same amount of upward motion at every point, right? If I move my input value out, because when I multiply a bigger number by 1.545, it increases more than when I multiply a smaller number by the same constant. And if to take an extreme case, down here at x equals 0, the function value on the blue curve is 0, 0 squared is 0. And if I multiply 0 by anything, I still get 0. So an important property of vertical stretches is that if the original curve is touching the x-axis, then the stretch is sort of pinned to the x-axis there as well. So you can regard the points on the x-axis as being sort of pinned down, and then the purple curve stretches from the blue curve everywhere else. If that k value is less than 1, so here's a simple example. Let's take a round number, like 0.5. Now the function values on the purple curve are going to be smaller than the function values on the blue curve. They're always going to be 0.5 times the value on the blue curve. So whatever the y value is here on the blue curve, on the purple curve, it should be half as high, right? So that is smaller. And as the blue curve gets higher up, that difference gets bigger, right? Because half of a bigger number is more than half of a smaller number. Okay, so that's the effect of a vertical stretch. So move around here so we can see, right? The lower the k value, the more it stretches towards the x-axis. And then for larger k values, I'm stretching away from the x-axis. A horizontal stretch, and you might even be able to predict the mechanism here, right? For a vertical stretch, we multiply the output by a constant. For a horizontal stretch, we multiply the input by the function, right? Notice the difference here, the k is inside the function instead of outside the function. And the effect of this is to stretch horizontally. All right, so let's look at this for a minute here. Let's take a k value that's sort of a nice number like 2. So the labels here again are off. I thought I had, oh, you know what we can do? I think this will fix it. There we go. And again, let's take k equals 2. Okay, good. Okay, so now if I want the function value on the purple curve, let's say at this point right here where my arrow is, what I need to do is I need to find the point that's twice as far out, right? That's 2 times x, and take that function value on the blue curve. So when I multiply the input by a number that's more than 1, the effect is to sort of pull the blue curve back towards the y-axis. We'll sometimes call this a compression instead of a stretch because we're kind of scrunching the blue curve down horizontally. Whereas if k is less than 1, take a k value of 1/2, now what happens is the blue curve gets pulled out or stretched out away from the y-axis, right? So as I move k around, right, as k increases, you can see that I get, right, so for large k values, I'm getting more and more of a compression. And for small k values, I'm getting more and more of a stretch, right? So when k is really small, I'm really stretching that blue curve out. And when k is on the large side, I'm really kind of compressing it, scrunching it in towards the y-axis. So let's look at a couple of the exercises again from the notes and exercises. So in 1.31, we looked at this algebraic formula in the previous video. And again, what I'm going to try to do here is compute formulas for these various transformations. Okay, so in the first one, reflecting through the x-axis, well, that's just a straightforward reflection. And to reflect through the x-axis, I want to put a minus sign outside the function. So what does that look like? I put a minus sign outside the function. F of x is this, x squared plus 3x. So be careful that you use parentheses and the minus sign hits the entire function, right? So when you distribute through the parentheses, you're going to get this as a result, right? So the graph of the thing that is in blue is just the original graph reflected through the x-axis. All right, what's the next one? Through the y-axis, again, that's just a straightforward reflection. This time I want to negate the input instead of the output to reflect through the y-axis. So what does that look like? Now I'm going to have f of minus x instead of minus f of x. Well, to evaluate this, we've done a lot of function evaluation, right? The input slot for f is here and here. So f of anything is anything squared plus 3 times anything. And f of minus x is minus x squared plus 3 times minus x. And then if you do a little algebra, you get this as your result, right? So that's a reflection through the y-axis. Let's see the next couple here. So through the origin, so we just said through the origin is both, right? That's a reflection through the x-axis and through the y-axis. So I'll want to do both here, put a minus sign inside and outside the function. So here's what that looks like abstractly. So I can do f of minus x, we actually just did up above, right? It's equal to this x squared minus 3x. So I'll replace the f of minus x by that. I still have that minus sign outside. And then when I distribute through the parentheses, I get this result right here. Okay, what's next? So here I want to do 2 different kinds of transformations, right? A reflection through the x-axis and a vertical shift down 3 units. So reflection through the x-axis means I'm going to negate the input, and shifting down means I'm going to subtract 3 from the function value. So what that looks like is this. Right, so here's, let me just go back to, right, so through the x-axis means negate the function value. So just this piece here, that's the reflection. And then when I subtract 3, that shifts down. Okay, so f of x is equal to this thing. So I'll just make that replacement here. So instead of f of x, I replace it by that formula. And then I just do some algebra, right? Distribute through the parentheses and you get your result there. All right, last one. Here I have a left shift and a reflection through the y-axis, right? So to shift to the left, I'm going to add 4 to the input. You recall that from the previous video about horizontal shifts. And then reflect through the y-axis, I'm going to put a minus sign outside the function. So what that looks like abstractly. So here, actually, you know what? Let's take our time here. Right, the first thing that I want to do is this left shift, right? So the left shift is accomplished by doing f of x plus 4, right? A little nicer, f of x plus 4, right? So that's just the left shift. Now, in addition, I have to reflect through the y-axis, right? So let's do this. Let's just get rid of this whole thing. This whole thing. Then we want to negate the input because we want to do a reflection through the, oh, I'm sorry, reflect through the y-axis, we want to negate the output, pardon me. So the function p of x, I think that's the name we want to give it. Yes, it is. Should be equal to this thing, but with a minus sign, right? So that's going to be minus f of x plus 4. And now I just have to fill things in, right? Here is the function f. It takes its input, squares it, and multiplies by 3. So this is going to be minus x plus 4 squared plus 3 times x plus 4. That should all be in parentheses like this. Right, so this thing right here, that is f of x plus 4, and then I have the minus sign outside. And then you could do some algebra to clean that up if you wanted and sort of FOIL things out. But let's leave that there for now and think quickly about this last exercise 1.32. And here we have a bunch of transformations of the graph of the function g of x. And it looks like here, oh, I see. Okay, so what we see in each of these is the graph of g of x, and what we want to show, what we want to add to the graph is this transformation. So this is going to be a vertical stretch because I'm multiplying outside the function, and because I'm multiplying by something bigger than 1, it's going to stretch up away from the horizontal. So what that's going to look like, in fact, here are a couple of stretches on the same curve. The blue curve is the original g of x. If I multiply by 1.5, that's going to stretch up because the constant's bigger than 1. And so that's going to give me something like the orange curve, right, which is higher than g of x. And if I multiply by something like 0.5, which is less than 1, that's going to sort of stretch down or compress and give me something like the green curve. Right, so along the green curve, the outputs are all half as big as the corresponding output on the blue curve. Notice that they are all pinned to the axis at x equals 0, right? Because if the graph touches the x-axis, then any vertical stretch is going to touch the x-axis in the same place. Okay, so that's actually the first two, the top two here that we talked about. So these now are the ones at the bottom are a little bit more complicated because they have multiple transformations going on. If I just focus on g of x minus 1, that's a right shift. So the graph is going to move right 1 unit. And then I multiply by 2, that's going to be a vertical stretch upward of 2 units. So what that looks like is this, right? So the blue curve is the original G. If I move it right 1 unit, then I'm going to get kind of a U shape, but the bottom of the U is going to be over here where my cursor is. And then when I stretch it up by a factor of 2, you can see the orange U is kind of narrower than the blue U because it's been, pardon me, it's been stretched upward. And finally, I keep doing that. Finally here, again, I have 2 different transformations going on, right? Actually, 3 different transformations going on. First, I multiply by 0.5. Well, we talked about that before. That's just going to compress it down towards the x-axis. Then I put a minus sign in front of it. That's going to reflect it through the x-axis. And then I add 5, which is going to shift it up. And the effect of all that is going to be something like this, right? So when I multiply by 0.5, I get kind of a shallower U. And then when I reflect, I get an upside down U down here. And then when I shift up, I get this upside down U, but shifted up 5 units. And you can see that the top of the U now is at the Y value 5 instead of the Y value 0. You might actually, as you're, I should have said this before, but it might be a good idea as you're watching this video, as we start an exercise, to sort of pause and then try the exercise yourself before we go through the solutions. Okay, so enough said about transformations. Let's talk a little bit about inverse functions, which is the topic of section 1.6. So here is a simple function, f of x equals 2x. And here are some function values, and this should be very elementary to you now, right? F of 2 is 2 times 2 is 4. F of 3 is 2 times 3 is 6. F of 5 is 2 times 5 is 10, and so forth. And here is another simple function, g of x equals 1/2 x. And again, I can compute some function values, right? G of 4 is 1/2 times 4, which is 2. G of 6 is 1/2 times 6, which is 3. G of 10 is 1/2 times 10, which is 5. And the thing to notice about these functions is that whenever f takes an input to an output, g takes that output right back to the original input, right? F of 2 is equal to 4, and g of 4 is equal to 2. F of 3 is equal to 6, and g of 6 is equal to 3. This always happens, right? No matter which pairs you take, it will always be the case that g reverses f, right? It kind of works in the opposite direction to f. And functions like this are called inverse functions, right? So these 2 functions are inverse functions. And what that means, to be a little more, so first, before we get to that, we'll use this kind of symbolism for an inverse function, right? So g is the function f inverse, right? So above, g is equal to, let's say g of x is equal to f inverse of x. And what this means, to be a little more precise, so here's this is actually saying the same thing we just said, right? The inverse function for the function f of x equals 2x is 1/2 x. We'll talk a little bit about how to figure this out down below, but for now, I just kind of want to understand what it means. What it means is that if f maps an input A to an output B, then the inverse maps B back to A. And this relationship always holds, right? If f maps A to B, then f inverse maps B to A. If f maps x to y, f inverse maps y to x, and so forth. All right, let's talk about recognizing inverses from tables and graphs. And then in some simple examples, we'll address this question of, if you have a function, how do you find the inverse? That can be difficult, but we can do it in some simple examples. All right, so suppose I have a table of values for a function like this one. So it's an input-output table. We've seen plenty of examples of this before. Let's answer some questions here about this function. So first of all, what is g of 70? Notice what this is saying is, if you give the function g the input 70, what is the output? So I go to 70 in the input row, and the result is 100. And so the answer here is that g of 70 equals 100, right? So this question doesn't really have anything to do with inverses. It's just an old-fashioned input-output table question. Okay, the second one here is asking what is G inverse of 100, right? So what does the inverse function map 100 to? Well, the answer is it will map 100 to whatever gets mapped to 100 by G. That is to say, G inverse works in the opposite direction of G. If G maps an input to an output, G inverse maps that output right back to the corresponding input. So if G of 70 is equal to 100, then G inverse of 100 is equal to 70, right? Then this is the same relationship between a function and its inverse that we were seeing up here between this function and its inverse, right? This reversal of direction. Okay, what is G inverse of 70, right? So this is asking what does the inverse map 70 to? So what I'm looking for is what does the function G map to 70? And the answer comes in this column right here, right? G of 30 is 70. That means that G inverse of 70 is 30. Okay, so here now we're talking about the composition. So remember our notation, right? When we write sort of functions nested like this, it's a function composition. What is G of G inverse of 70? And I'm going to handle this the same way we handled compositions before. We start on the inside, right? What is G inverse of 70? Well, we just answered that question. It's 30. So this is going to be equal to G of 30. Oops, 30. There we go. And what's G of 30? Well, this is just a straightforward evaluation question for the function G. Here is where G of 30 is, that's equal to 70. Notice that G of G inverse of 70 is just equal to 70. And this is no accident, of course, because inverses work in opposite directions. Whatever G inverse maps 70 to, G is going to map that right back to 70. So you can sort of understand that abstractly, or just go ahead and compute this and figure it out. Works as well. Similarly here, G inverse of G of 40. I'll start on the inside with G of 40. So let's copy this whole thing here. So this is going to be G inverse of what's G of 40? G of 40 is 80, right? So this is G inverse of 80. And what's G inverse of 80? Well, G inverse maps 80 to whatever gets mapped to 80 by G, which is 40. And again, we see this phenomenon where when you compose inverses, they sort of undo one another and you just get back what you started with, right? G of G inverse of 70 in the previous example is equal to 70, and G inverse of G of 40 is equal to 40. And again, that's not an accident. Okay, let's talk about recognizing some inverse values on graphs. So here's a piece of a graph of a function h of x. Let's estimate h of 1. So notice in this first one, there's no inverse here. It's just estimating a function value. So all I have to do is go to the input 1, which is right here where the cursor is, and figure out what the output value is. And it looks like that output value is a little more than 4. I'll call that 4.25 or so. Okay, h inverse of 1, we have to be a little bit careful of, right? So h inverse maps 1 to whatever is mapped to 1 by h. So the question is, what is mapped to 1 by h? Well, in order to figure this out, I'm going to look for the output 1, not the input 1. And the output 1 is over here on the vertical, because outputs are on the vertical axis, and ask what input gets mapped to that by h. And the answer is over here, this input right here, which is 2.6 or 2.7 or something like that, right? So I would estimate 2.7. That is, to sort of flesh this out a little bit, it looks like h of 2.7 is equal to 1. And that means that h inverse of 1 is equal to 2.7, right? Because a function and its inverse go in opposite directions. Okay, what about finding inverses? Let's say I have a function like this. How do I figure out what the inverse function is? And the key is this relationship that if y is equal to f of x, then x is equal to f inverse of y. So if we call this thing y, if we let the output value be y, which is what we usually do, then we can figure out the inverse with a little bit of algebra. I'm going to take this equation, y equal 3x plus 5, and solve for x, because I'm looking for an equation that looks like this. Well, that's not too hard to do here. Again, if this function were more complicated, that might be a difficult algebraic task. But here it's not so bad, right? All I have to do is subtract 5 from both sides, and that gives me y minus 5 equals 3x, and then divide both sides by 3, and that gives me x equals y minus 5 over 3. And right now I am looking at, on the left, y equals f of x, this equation, and on the right, x equals f inverse of y, this equation. So that means this thing right here is f inverse of y, and the input letter doesn't matter, right? Whether you call it f inverse of y or f inverse of w or f inverse of x doesn't make any difference. So if this pink thing is f inverse of y, then f inverse of x is this function, x minus 5 over 3. And we have found a formula for the inverse of this function. Okay, so let's quickly look at a couple of exercises. 1.38. Where's 1.38? Here we go. So these are both exercises in finding an inverse function, right? So I'm given a function, I want to find the inverse. Let's start with this one, right? F of x equals 3 plus x. So again, what I'm going to do here is first solve y equals 3 plus x for x. So that's not hard, right? I subtract 3 from both sides, and I get x equals y minus 3. And then on the left, I'm looking at y equals f of x, and on the right, I'm looking at x equals f inverse of y. And whether I call the input variable y or x or q doesn't make any difference. So f inverse of x is equal to the function x minus 3. Okay, straightforward enough. Let's try the same exercise for this function, 5 plus 2x. So again, whoops, same start. I start with y equals 5 plus 2x. I try to solve for x, right? So that's not too bad. I'm going to subtract 5 and then divide by 2. Right, so if I subtract 5, I get y minus 5 equals 2x. And then divide by 2, and I get this formula right here, y minus 5 over 2. On the left, I'm looking at y equals f of x. On the right, I'm looking at x equals f inverse of y. And I conclude that f inverse of x is x minus 5 over 2. And I think you can leave that as it is in the blue shaded expression here. I do some rearrangements. I'm not sure why, actually, just to sort of get some algebra practice, I guess. Okay, and then one final note about inverses is that not every function has an inverse. And a good example is the function f of x equals x squared, right? So if this is our function f, then f of 2 is 2 squared, which is 4. And f of negative 2 is negative 2 squared, which is also 4. Okay, all fine so far, but if we were going to have an inverse to this function, we wouldn't have a good way to define f inverse of 4, right? Because the inverse has to be such that it maps 4 back to the input that was mapped to 4. But if there's more than one of those, then this function doesn't know what value to take, right? Should it be 2 or negative 2? So functions like this simply don't have inverses, and we'll sort of leave it at that, right? In order to have an inverse, a function can never map multiple x values to the same y value. And that's what's happening here, right? I have the x value 2 and the x value negative 2, both getting mapped to the same y value 4. So on a graph, let's look at this, pull the graph up here too while we talk about this. Here's the graph of y equals x squared. Here's x equals 2 over here on the right, right? So that's the point 2 comma 4 where my cursor is now. And this is the point negative 2 comma 4 where the cursor is now. And the visual sort of manifestation of this feature that both of those inputs are mapped to the same output is that they're both on the same horizontal line, right? Because they have the same output value. So if you have two values on a graph on the same horizontal line, the function won't have an inverse. So in order to have an inverse, it has to pass a horizontal line test. And we briefly talked about horizontal line test way back in the first section. Functions that pass a horizontal line test are called one-to-one. So in order to have an inverse, a function has to be a one-to-one function. And we can spot this visually by applying a horizontal line test to the graph. Okay, what comes next here? Oh yeah, and just a quick word also about one-to-oneness in tables. Here is an example of a function, an input-output table for a function that is not one-to-one. So how do I know this function is not one-to-one? Well, it would have to map multiple inputs to the same output. And you can see that happens here and here, right? I have two different inputs, right? The inputs are on the left, the outputs are on the right. The inputs -3 and +2 both maps to the same output 10. So this function is not one-to-one and won't have an inverse. On the other hand, here's an example of a function that is one-to-one, or at least is one-to-one for as much information as we have about it, right? So we only have 6 input-output pairs for this function, but at least based on the information we have, this is one-to-one because I don't have any multiple outputs, right? I never have, sorry, I don't have any repeat outputs, I should say, pardon me, right? I don't have multiple inputs mapped to the same output. Okay, this is section 1.6 on inverses. So go ahead and practice this stuff and take good care of yourselves.